Viel Spaß. Okay. So welcome for this year's distributed databases. For those of you who are surprised, this lecture will be in English because it's part of the ETIS lecture program. So I guess you two guys are ETIS, that's right? No, you're not. And that's funny. Okay. Good. So nobody from ETIS is here. Doesn't matter because you're doing video recordings and they will need it in English. Therefore, well, the lecture will be in English. I hope it works out. If you have problems understanding me, just, interrupt me and ask something. Good. So, what will happen this year or this semester? This lecture will be for 14 weeks. We will start today, obviously. And the last day of the lecture will be indeed in the last week of the lecture time. Every week we have 2 hours and 15, I think, so basically 3 academic hours from 9:45 to 12:15. And of course we are skipping the excursion week because, well, nobody is doing lectures there. So basically, this is a master lecture. So we are doing the lecture itself, and in the lecture we are having these detours. Those of you who already had a lecture with EFIS know that the detours, that's usually some stories we just tell. I mean, it's part of the lecture somehow, but it's not part of the exam, so it's not something you need to study. It's more for bringing a broader view on the topic and, well, basically some historical facts or how it's used in industry or what funny things you do with a technique. So it's not something you need to prepare for the exam. So more or less the workload should be of a normal lecture with 2 hours. We are not doing real homeworks. So from time to time we are uploading an exercise sheet, which you may do, but nobody has to do any homeworks because, well, we are not allowed to force people anymore, and since that time nobody's doing homeworks anyway. So in the first few years where we offered full homeworks, we got like 1 exercise sheet or 2 exercise sheets per month or so that is not really worth the effort. So you can have a look at the old exercise, do it, or, well, don't. Basically that means we won't also correct them, but if you have any questions, of course, we can answer them. So it's fully voluntarily. Good. The exams will be oral, so no written exam. For those who already did an oral exam, the emphasis on the oral exams is basically on topic understanding. So it's more about why are things done, what is this about, why should you do it like that and not in a different fashion. So it's not really about like written skills like we do it in RDB1, where you have to write down SQL statements or algebra statements. Therefore, the lack of exercises is, I think, not a real hindrance, because the proper way of preparing for that exam is basically taking the slides, reading through them, and then asking yourself all the time the questions, why should anybody do it like that? And what is this about? Why should anybody need that? If you can answer these questions, I think you are well off for the oral exams. Good. That's it for organizational issues. You can download the videos in case you skip or miss a lecture from our webpage. I guess most people already found that. We try to upload the slides usually on the evening before the lecture, so basically Tuesday evening. And we try to upload the videos on Wednesday evening, sometimes Thursday morning, because it takes a long time encoding and recoding these things. Good. What is this lecture about? This lecture is called Distributed Data Management. I think in the Model Handbook it has an older name, something like Verteilte Datenbanken und Peer-to-Peer, whatever, something like that. But both describe rather well what's going on. So basically we will have 3 major topics which we will cover for a couple of weeks. So the first 4 weeks we will do distributed databases. The next, I think, like 5 weeks or 6 weeks we are doing peer-to-peer systems. And the remaining 3 or 4 weeks we are doing cloud storage. This will be a lecture on the foundations of distributed databases. So we won't do the bleeding edge new cool things because, well, you will have a hard time understanding what they're doing anyway if you're like in the basics. Therefore, distributed databases, that's the topic which came up in the 80s when people realized that normal database servers don't scale well, both with as in press, so they don't scale with the workload nor with the performance. So people started doing database servers on multiple machines, which turned out to be very, very complicated with a lot of trouble and hurdles. And that was a major topic of the 80s and 90s. And then the web came on. So we had all these web scale information systems, so companies like Yahoo, Google, Amazon entering the field, and they had very different problems. So the early web companies couldn't really work with databases because they were too strict in their design. I mean, we will talk about that for quite a while. So they developed new types of techniques. And at the same time, I mean, those of you who are a little bit older maybe remember, peer-to-peer systems became popular. Especially so from 1998 till 2006, that was a big hype, you know, like internet piracy, where people use stuff like BitTorrent or Casa, eDonkey, you name it, to steal whatever you could get your fingers on. And this is all based on peer-to-peer systems and peer-to-peer technology. There we are putting a big emphasis on. Why should we do that? Why should we care how to pirate stuff on the internet? Well, thing is, those peer-to-peer systems, they all started out as academic prototypes. They started out as prototypical systems of how to do coordination and file association and basically data handling in a distributed and highly volatile environment. So basically here we have the setting of potential 500,000, 1 million nodes which can join the network, leave the networks, which can have very bad connections, which can be malicious, and people were looking for solutions how to deal with that environment. And the only immediate application you had for that was basically internet piracy. However, that changed after a while. So later, when it comes to cloud storage, which, well, used to be one of these hot topics of, let's say, 2011 to 2014, where everything was in the cloud and you became insanely rich when you did cloud computing and cloud management. So nowadays, the hot topic is big data. It's again a word which doesn't mean a lot. And big data just means you have a lot of data and basically you don't know what to do with it, and you just store it because that's the only idea you currently have. And you do it usually in cloud systems, and basically all these things. So cloud systems are just an amalgamation of peer-to-peer technology with traditional database technology. And we will see that when we do Amazon Dynamo, which will be in week 11, which looks exactly like stuff like Nutella or eDonkey. It's basically the same architecture. It's the same architecture which drives piracy, which now runs in Amazon data centers. They just relabeled it, and now it's not called peer-to-peer system, but, well, highly adaptable cloud storage. But basically, it's the same technology. This is why we have it in the lecture. And, oh, that was bad, sorry. Hey, shouldn't do it like that. Yeah. Okay, good. So these are the 3 topics we will be covering in the next 14 weeks. And in the last 3 or 4 weeks, we indeed do a lot of the more modern systems like Google Spanner, which is now the back end of, well, basically all Google. We will do Amazon Dynamo, which is the high-speed database, well, database-like thing Amazon introduced in 2007 and started selling as a product, I think, since 2012. And one of my favorites there is the marketing video Amazon made. Maybe we'll come to that. It's really amazing because basically what they did is they took this distributed peer-to-peer system, somehow played around with it, and then they had a team of marketing people go over it, and they made this really cool video where they show that this is the brightest invention since, well, forever basically. And they sell it for rather expensive now even, so it's a very old idea which, well, bases on stuff which is 10 years old or 15 years old. Good. Literature. If you want to read some book or literature, it could be these. I would not recommend buying them. So if you want to read them, I think most of them should be in the central library, and all of them are in our institute library. So if you feel the urge to read these books, drop in and read them at our place, because, well, some of them are not really expensive, but I think that one, for example, it costs quite a lot of money, and I think it's not useful enough to satisfy or justify 100 euros for that book. However, we have it, so if you want to read it, do it at our place. Why are these books only partially helpful? Well, that is because these books just focus on very small topics. So, for example, that book over there, it only does distributed database systems. And they do it from, well, the traditional way of doing databases. So that book will be like the stuff we do in relational databases too. So this very typical, hardcore, old school way of doing databases. I don't know, did anybody attend relational databases too? RDB2? You. You're the only one? Really? Ha! Is somebody planning to do relational databases too this semester? Okay, so you guys will see that there's quite some overlap between relational databases 2 and 1. So originally this lecture was intended as a follow-up lecture of relational databases 2. However, with the new module handbook structure, this doesn't work anymore. So basically now it's a standalone module, which works by replicating the stuff in RDB2. So you will see a lot of stuff we will do here and in RDB2. So usually here the RDB2 stuff is just a very, very long detour, like, oh, in case you forgot, this is how it works, so that you have an idea. So for you guys who do RDB2 will be significantly easier when you already understand that, and vice versa, I guess. But for the others, I think you should be fine. We are doing this hardcore database stuff only for 3 weeks and only on a very shallow level, so don't worry, it will work out. Anyway, when it comes to database design, we have these lectures, Relational Databases 1 in the bachelor and Relational Databases 2 in the master's. These lectures deal with the old school and typical way how to build a database system. So there had been a theory how you should do that, which started in the 70s with an IBM research project, which was System R. And IBM in the 70s invested a lot of money in how to do database management in a better fashion. Before that, there were of course databases, but they didn't have a proper data model. So they had network models which wrote stuff in some kind of a tree, which was very hard to work with. And one of the innovations of the 70s was the invention of the relational model. So basically having tables, right? So where you have tables with foreign key constraints and with query languages like SQL. And in that time, a lot of stuff was invented we cover in RDB1. So basically IR modeling, data modeling, this table style stuff, SQL, relational algebra, that's all from that time. And the first prototype which was built was the System R from IBM. They built it as a research prototype, which worked pretty well. And a lot of the ideas invented for System R are still in place in nowadays modern systems without, well, only limited adaptations. So basically, the core design in databases didn't change for a long time. And you can see that one of the oldest software systems which are still running is IBM IMS. IBM IMS has been around since the 60s. That's the database system which fired up the Apollo program of NASA. And it was developed for Apollo, and that thing is still running at the core of a lot of banks. That piece of software is like 60 years old now, or 50, something like that. And it's really ridiculous. There's a piece of software running for 50 years, only with small maintenance and small adjustments so that it doesn't crash on more modern hardware. And sometimes it's even running on the hardware from the 70s and 60s, so where a lot of banks still have these bunkers below their headquarters, where they have these really old mainframes which they bought 40 years ago, including a huge storage room with old replacement parts. So in order to repair these things, because nobody dares touching these systems. So a lot of that stuff is very, well, traditional. And it took a long while until people started building a new design of databases. And I think that started a lot in 2003, 2004, 2005. So basically for 30 years, the architecture of databases didn't change a lot. They are all clones of System R. And if you know what happens with System R, though, that thing disappeared. It was just an academic prototype. And one guy basically replicated it. And that clone was called Oracle Database by Larry Ellison, and we all know what happened with that. So now this guy is one of the richest people on the world, just a little bit behind Bill Gates, and his company is super, super, super rich. And that's because he was selling that idea. IBM, who built it and invented it, well, somehow took another 10 years to make a commercial product out of it, which is DB2, which he probably used in select courses in the last semester. Good. Now, this lecture breaks from that design. The first few weeks will fit into that traditional design space. So this is stuff Oracle does, DB2 does. So this is System R style databases, including all the positive and negative properties. Then, peer-to-peer, we completely break with all these ideas and start from the scratch, and that results in a very new way of implementing databases, which is very different from the traditional path. So nowadays we have database systems which are traditional, Oracle, DB2, for example. We have smaller databases which are traditional, stuff like SQLite, for example, or H2SQL. And we have databases which have a very different architecture. A lot of that stuff comes from the ideas in this lecture. That will be stuff like SAP HANA. I don't know if you heard about that. SAP? Everybody knows that, I guess. They used a modified version of MySQL for quite a while and bought in licenses from Oracle. And Oracle doesn't get rich by accident, so they get rich because they charge other companies ridiculous amounts of money. So SAP had to pay a lot for the Oracle licenses. And as SAP is rather large and they have an own research branch, one day they decided, okay, this really sucks, we shouldn't pay that much money to Oracle. How about us building our own database? And they basically did that, and that is SAP HANA, which is one of the first fully commercial databases which has a very different design, paradigm behind it. So SAP HANA works differently to Oracle and DB2. And in the same sake, we have Google Spanner, Google Bigtable, we have these things like HBase, which, built on this distributed paradigm. Good. Anyway, I was talking about literature originally. Most of the stuff we do in the later chapters will be based on papers and not really on books. So if you have the urge to get more information, look up the papers we're referring from time to time, look up the topics just by Googling. That should work out rather nicely. Good. Now, I talked a lot about this traditional style of databases and how it changed. So what exactly does that mean? And then basically that will be the topic of today's lecture. So today I will give an overview of all the three topics we will be covering. First is the distributed databases. As I already mentioned, relational databases are a very successful but very old part of computer science, which started in the 60s, and mostly it was driven by the finance industry and the military, because those were the people who had the highest stakes into storing data in an efficient manner. Well, let's use the example of banking systems. What does banking do? Banking is a very, very simple task in itself, which basically could be done with paper. I mean, for a lot of centuries you did it with big ledgers and books where people wrote stuff down in tables. And this was directly translated into the digital world. So basically, our databases mimic a huge ledger collection. So basically, a lot of worksheets, a lot of tables where you enter data and subtract and add stuff and transfer numbers from left to right. So something like that. And we had these database management systems. Back then, these systems were these really huge machines, so mainframe machines, which were running a central a centralized database management system. So basically that's a single core, single thread application, which by using some kind of time shifting somehow allows a lot of users to work simulated concurrently on the system. And the traditional architecture of those databases are that you have a single hardware node. So here's a query thing. Then you have a query processor. The query processor is the software part which takes a query, so for example in SQL, and then translate it to relational algebra. This is why we teach people relational algebra, and relational databases 1. Then optimizes that relational algebra statement into a more efficient form, which is also something we will do in this lecture too in a very limited fashion. And then accesses the data. Access to data usually goes over the storage manager, which takes some data from the actual data stores. And then we have this dubious transaction manager here. The transaction manager is that part which is responsible for keeping the consistency of the database. So for doing transactions. And transactions, so we have 3 features I mentioned here. So one is optimization. The other feature is transactions. These are 2 core features which define databases. And these are also the 2 core features which later got dropped and which became extremely uncool in the mid-2000s, and which now, and that's really funny, because when you go to research conferences and databases, in 2005 and 2006, a lot of talks you were hearing were like, oh, let's get rid of transactions, let's get rid of optimization, just do it with new hardware, with new technologies, blah, 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 everything will be better. People did that for 5 years or 6 years, it worked out rather well. But now a lot of tries come back with, oh, we need transactions back. So basically now all these things get re-implemented again and again using the same ideas which have been around for 30 years. It's quite entertaining to see that. Good. The transactions are just a bundle of operations which form a package, and that package has certain guarantees. We will talk about that a little bit more later. So basically, you have a guarantee that these commands and the transactions do get executed without destroying your system or destroying your data. Good. Back then, as you had in single node, all data was stored in the same machine with same connections to the same machine, and transactions could just cover within the machine, obviously. Good. But later we had a need for branching out. So basically the first thing what happened is that a single computer is not enough to store all your data, and you need more systems to attach more hard disks to store more stuff. Then you had the next problem that you had companies which started to have branches all over the country. So for example, banks, you have a branch in each city for a given bank, and of course somehow these branches need to communicate. And one of the early approaches was that these branches had a wire back home to their main branch and basically phoned in, and everything was done on the central server, which was sitting in this huge bunker and which was a very, very expensive machine. But that's obviously not a brilliant solution. So later you switched here to distributed databases where each branch had its own database system which synchronized with the central one and, well, did a real distributed systems. Also, you had to share resources. So basically when you had multiple hardware systems, you needed a technique to, well, basically access the additional computational power, the additional storage power into a bigger and more powerful system. But traditional techniques for implementing databases don't work with that. And we will later see why. Also, that's a very interesting part. You needed more fail safety. So the idea is if your one system crashes, a centralized database systems, as you guys who do relational databases too will learn, put a lot of emphasis on recovering data. So there are a lot of techniques for recovering a broken hard disk, for recovering, some write failures and these things. So usually a database system should never break, unless of course you destroy the whole thing. I mean, if you just burn down the computer and all the hard drives or tape drives or whatever attached to it, then obviously the thing is gone and no software will ever recover that. Therefore, the only way of preventing real disasters, stuff like flooding, fire, earthquakes, meteor impacts, something like that, is distributing the stuff. So basically you have multiple sites all over the world and you're duplicating and replicating your data all over the world, and if one complete data center disappears, it's not too bad because you have copies on it someplace else. And that's of course for highly critical applications like banking a very interesting thing. And now if you see advertisements for cloud storage, like Amazon does it, they also do advertisements like, okay, you store your data with us and we will replicate it over the world and it can never get lost because there will be tons of copies everywhere, and no, it won't get lost. So who did relational databases 1 here at TU Braunschweig? The other guys are all coming here from the master from some other place? Okay. Anyway, in this introduction course in databases, in our case it's relational databases 1, you probably also have an introduction into databases. Typically, you do stuff like normalization, I would assume, right? Where you say, okay, you have this database schema and now we have to normalize it. And why should you normalize a database schema? And that's also one of the more popular questions in the exam. Yeah, you're normalizing the database schema in order to reduce redundancy. Why should you reduce redundancy? Yeah, because if you have redundant data, you can run into a lot of problems when writing and reading, because you can, well, basically create inconsistency rather easily. And a lot of people mistook that for redundancy is bad. So somehow a lot of people who finish the introduction course have this idea that reducing redundancy is always a good idea and redundancy is evil and should be vanquished. I mean, there's some truth to that, but here in this lecture we will see we have an extremely opposing view on that. So here we will have a lot of redundancy, and redundancy is a good thing. And the more redundant our data is, the better, because then it's more safe and more secure and you can potentially do faster queries. Now the big question is, what happens with all the problems we are talking about in the introduction courses? Well, of course they are still there, right? I mean, of course we have problems with consistency when writing on highly redundant data. Now the big question is, what do you do then? And you have two solutions there. One solution is, well, you need very clever techniques preventing any problems. That's what distributed databases do. Or you say, don't care. That's what cloud storage does, right? They just say, whatever problem there arises, I don't care, it will be fine in the end. Good. So, what is this first topic about, distributed databases? That is a topic of integrating several traditionally designed relational database management systems into one big distributed database. So this is really about traditional SQL relational databases. We will have all the features we are used to from the introduction courses, like having a relational model with tables, having SQL, having a query optimizer, having transaction, having recovery, you know, all these features which we are used to from databases. That's our first topic. Now just with more computers, right? Good. What does that mean? Basically, we have a database where we have multiple nodes or computers. It could also be multiple nodes within a single computer. So assuming you have a multi-core processor, you would actually need a distributed system to take advantage of a multi-core processor. Because those techniques we teach in RDB 2, Relational Database 2, they are basically optimized to run on a single thread, on a single CPU, which of course it doesn't make any sense anymore, because Intel now is shooting out this 10-core system, 16-core system, 32-core systems for the server side. Just running on a single core doesn't cut it anymore. But as you guys later will see, those techniques cannot easily adapt to multiple cores. So basically, a multi-core system is already in need of a distributed database management system. And as I claimed, it's still a real database. And the problem with that is you get all these database features. However, you're paying for these features by, well, basically loss of performance and a very strong loss of flexibility. And the later systems like peer-to-peer cloud storage, they, change that trade-off. So they trade off features for more flexibility and performance. So they don't care about feature sets. Good. What are the features we have? So we have the features of having controlled redundancy. Controlled redundancy means you don't have non-redundant data, but you have redundant data in a way that you know what is redundant and you have full control over it. So controlled redundancy, you still have data normalization. It's not that normalization goes away. You still have this really neat and cute schema, these schemas we do in the introductory courses. You just replicate them a couple of times, but still it's a very clean, high-level data model. If we now talk about systems like Google Bigtable later, you will see that these things don't have a proper data model anymore. And those document databases, basically there you just throw in whatever you have without any schema, without any data design. That's not the case here. Here you still have proper normalized database schemas in a well-designed fashion. You have consistency constraints, you have integrity constraints. So you have an idea what consistent and integrated data actually means, right? So you are making assumptions about what your data should look like and what is the bad state of your data. You still have powerful query languages. Well, in this case, it will be some variant of SQL. And you have a very effective and secure data sharing, backup, and recovery techniques. These are the features we want to have in a database and always in a distributed database. Good. What does that mean? Well, well-structured data, yes, of course, that's probably something most people have seen and one way or another. So basically, you have a proper data model here in entity relationship diagram with foreign key relationships. So for example, a customer has multiple accounts and the account has an account number with a primary key, and the customer has an ID, and this can be transformed into tables. This typical, okay, now we need a table out of that, then you will have some foreign key constraints, but still that thing is extremely well designed and specified what you need. And the problem here is you have to specify these models at design time. After a system is implemented and after your software is running, traditionally it's very hard to change some things there. So if you have a business case, they actually don't have any clue whatsoever what you need to store in the future. It will be very, very, very hard with a traditional relational database. They have to design a schema up front, right? And that's also one of the reasons why in banking, relational databases are extremely popular, because everybody knows how banking works, right? And you just design your bank system, deploy it, and then you use it for, well, 100 years or 50 years or how long. While for a lot of these web page companies, those companies like Google, Yahoo, Amazon, when they first came into the market, they actually didn't have the slightest clue what they might need in 2 years, right? And for them, something like that is actually not a feature, it's a liability. And they built systems back then which didn't have a data model, where you can just insert new attributes during runtime. They actually don't have attributes at all, they just throw in objects or networks or documents, whatever, or just key value pairs. I mean, a lot of these new systems are just based on key value pairs. So basically like a huge hash map. Good, but here we still have that. One advantage when you have a very clear data model is that you can actually work with queries and optimize queries. The first thing you could do is when you have a table and primary key constraints is building indices, so building an index. So that's one of the major topics of relational databases too. And the idea of an index is actually super simple. The idea of an index is if you have data stored in a structured fashion, let's assume like in a library, think of you have a big encyclopedia in a library before you have Wikipedia and these things. And you have these 12 books, right? And all knowledge was written down in this huge encyclopedia distributed over 12 books. How can you find something there? It's very easy. First thing is you just don't write stuff down randomly, but you write it down with a certain system. For encyclopedias, it was you write it down by the first letter of its name. So basically, these things are sorted by alphabet, right? And then it's very easy how to find something. If you're looking for Braunschweig, you just need to find the book which contains the letter B. Then you have on the book bags, you have this little lettering system. Okay, this book contains A until AZ. Next one contains BA until CD, and so on and so on. And then you look at the back of the books, and so, oh yeah, this one contains BR for Braunschweig. You take out the book, and then in that book you can just flip over because everything is sorted by alphabet. And when you are at Bonn, you just have to go on because Bonn is before Braunschweig, I guess, in the alphabet. And if you end up at, I don't know, BZ something, whatever word has BZ in the beginning, you flip too far and you can go back. That's an index, right? It's just ordering stuff and having some shortcuts for finding things. I mean, we don't have to concern ourselves how it works in a database system, but as you can see, having an index can speed up stuff rather significantly. Just imagine trying to find something in an encyclopedia which is randomly, well, not sorted. Basically, every topic is somewhere in one of the 12 books and you have to search through everything manually without any help. Horrible, right? Index, just sorting stuff and having some shortcuts. Not really a major topic in this lecture, but it's there, and distributed databases can use indices to quite a strong effect. Good. Next big feature we have with distributed database is data abstraction. That is the abstraction of the data model, like the model we have seen before, and the actual storage of data. So basically, for the user of a database system, it's not really important how and where data is stored. So you don't have to concern with yourself with stuff like character encoding. Now, it doesn't really matter if some bit sequence means now an UTF-8 character or an ASCII character. If you encode numbers, I mean, there's a whole science behind how to encode floating point numbers in binary. Right? That's not an issue we have to address here, because that's all stuff the database system does for us. Because there's this really neat typed and modeled data model where we don't have to care about translation of binary data as it's stored on the hard drive to application data. This may change quite tremendously in newer systems. So if you have a new database like the early versions of Amazon Dynamo, that thing was just a key value store, right? You had keys, so for example, customer IDs, and you had values. And these values were something like serialized Java objects. Now, I guess most of you guys can program in Java, and you know there's this serialized function in Java where you can just do a binary memory dump of an object you have in the main memory and serialize it somehow to the hard disk. Right? And then you have this object which is, well, binary, but which is completely unreadable by anybody but you with the exact same version of your software. And as soon as you change your software or change your class diagrams, the whole binary data becomes useless. That's basically the situation you have later in the newer distributed database systems where you don't have this insulation between data models and data storage, right? Because here you directly modify how data is written down to the disk in binary. It's a really annoying problem dealing with binary data. Obviously, distributed databases don't do that. Databases don't do that neither. Basically, you can happily move around your tables from different hard drives to other hard drives. You can add new columns, remove columns. So in a certain way, you have some flexibility. Not full flexibility, as I said before. Still, you have to keep to your model somewhat. I mean, adding a new column is nice, but still entails a lot of problems. But you have certain flexibility here without caring about the problem, because the system does it for you. Then we have use. Use is computed abstractions from your data. So data is stored in one way, and now for different users, data is aggregated and presented in different ways, and in a way which is useful to the people. So for example, the manager might get just the aggregated data with the overall sales numbers per month, while, I don't know, an office clerk might get the raw data with single transactions and single account movements. Okay, that is use, another feature we have in traditional databases, and which we want to keep in distributed databases, but we don't care about that in these new type of databases like cloud storage. So simplest type of view is simple projection, right? You just have the original table, and one guy gets the green projection where you just get the savings account, while the other guy just gets the checking accounts, and you're basically having two views which decide based on that property where data goes and how it's presented. Good. Now it becomes more interesting. Sharing. One of the core features of traditional databases was that you want to support a multi-user environment. And if you imagine that in the 70s, when that stuff first came out, you had a central single system, and then you had a huge number of people who want to use that system concurrently. And these systems were single-threaded. So you had a single thread, you had a lot of people using it concurrently, and it should look like it's working concurrently. So basically one thing you do not want to have is one guy, let's say the manager, who is interested in a big aggregated query, so like, oh, give me the sales of the last 10 years, aggregated and then sorted by region and product, blah, whatever, and that query runs for 3 days, which is really not untypical. As we cover in the lecture, I think, data warehousing. This is a warehousing query and an analytical query. These things can run very, very long time. And while that query is running, other queries shouldn't get blocked, right? Even though there is a query which runs for 3 days on a single thread, other queries still should come through. And then we have the same problem like the operating system guys. They have to do transactions here. So we have to do some kind of concurrency. And for those of you who did you actually do that? Operating systems and scheduling and these things? No? I don't know. Back when I was young, everybody had to do these things. Now, anyway. Basically, that's the problem when you have multiple threads running in an operating system and you have more threads and more programs than you have CPU cores. How do you do that? Basically, that's the birth of multi-threading and multitasking, which became, well, an important issue in the late 90s. And again, became very popular in 2008 and 2010 when we had these mobile devices. Maybe you remember that the first version of the iPhone and iPad, they didn't support multi-threading and multitasking. You just always could run a single application because, well, it was a single-core machine and the operating system back then didn't have proper scheduling. That was very annoying. And you had a lot of these Apple fans who always claimed like, but you don't need transaction, it's a new age, now we do single thread and focus on single task. Transactions, that's so old school, blah, 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 whatever. But as soon as Apple somehow got around to this problem, of course, multi-threading became a super important feature and everybody wanted to have that again. That's the same problem here, right? So the multi-threading problem in operating systems and the transaction problem in databases, it's basically the same with some, well, adjustment, but it's not too different. So having multiple queries running on the same machine, which has less computational threads than you have queries, how can you schedule that, and how can you prevent that these multiple queries which run simulated at the same time get into the way of each other? In traditional databases, you do the same trick, like an operating system, you schedule. Scheduling means you take multiple parallel running threads, which have single commands, a command chain for each thread, and then you take out the single commands and just order them into a single command execution, right? So you have stuff which is supposed to run in parallel. You only have a single CPU with a single thread. So you just shuffle in and just do first something for task 1, then something for task 2, then something for task 3, then again something for 1, for 2, for 3, and then these things will run in parallel. I mean, it's not real parallelism because you still have a single thread, but it will look for a user like it's running in parallel, right? This is what relational databases do. Here, we of course have the luxury that we don't have to do that because we indeed do have multiple nodes. We do have multiple threads. So we do have multiple CPUs which can work in real parallel fashion, right? So here we have in the 80s the first time multiple machines which can work either on multiple queries in parallel or which can distribute a single query over multiple machines. And this, of course, creates a lot of problems because queries might interact with each other or might destroy each other's result, basically might overwrite the results of other queries and might lead to a lot of inconsistencies. In order to prevent that, we have this transaction theory, which basically also goes back to the 70s. And there you have this ACID transactions. I think that's something everybody has heard before, right? Who has never heard about ACID transactions? Good, everybody has. That's good. So ACID transactions. Here you have this atomicity. Basically, transactions should be executed in its entirety or not at all. You have consistency, that a transaction should always start in a consistent state and should finish in a consistent state. In between, data may be inconsistent. However, it must be prevented that anybody can read the inconsistent data in between, right? Because it's atomic. Yeah? So you have, if from one consistent state to another consistent state, you have isolation. You have to prevent that multiple transactions get into each other's way. And you have durability, basically, when a transaction claims it has written and committed a change, that it's really written and committed, and, well, that this is true. These ACID transaction properties are very, very, very expensive to maintain. So building a database which actually does this ACID takes a lot of effort, and it also takes out a lot of performance. And for many use cases, it's very important to have ACID, right? If you're a bank and I'm wiring money from my account to one of you guys' accounts, and then somehow the money gets removed from my account but never appears at yours, and the money is just gone, and I go to the bank and say, hey, where's my money? And they're like, oh, computer problem, transaction problem, it just disappeared, whatever, sorry. That doesn't work. So this type of transaction is super important to prevent that. However, not everybody is a bank, right? So if you have stupid stuff like Facebook updates, or I think the first guys who did that was Yahoo with their first social network in 2001, and there was a famous talk about the Yahoo database designer who claims that transactions for their environment are completely useless because he claimed our users are just doing stupid stuff with our system, like doing pictures of their cats and talking about that they just ate a banana. It does not matter at all if that information is delayed or lost. Nobody will care, nobody will notice, so why should we care about securing it? Yeah, I mean, there's some truth to that. And if it takes 5 seconds or 10 seconds to update your data status on Facebook, whatever, nobody cares. And if multiple persons access your Facebook account at the same time while you are just changing your status, and I can see the change and the next person can just see the change in 10 seconds, whatever, right? I mean, it's not important. It's just important that in the end, your change will be reflected to everybody. And basically, if that simple observation leads to a different transaction model, we will cover that in lecture 10, I guess. transaction model for this newer type of web databases, which is called base transactions. See the wonderful joke behind that, acid-based, blah. Computer scientists are so funny. And these base transactions are opposed to ACID in that way that eventually all updates will be executed and eventually your data will be consistent. However, it can take quite a while until the state of consistent data is achieved. And in between, it can be complete chaos and nobody cares, right? And if you have a transaction model like that, of course, you can build databases which are significantly faster and which can scale much better. Oh, I'm talking too slow, sorry, or too long. Yeah, good. Then, what's the goal of distributed databases? Basically taking all these database features and transforming them into a distributed environment, including, but with some additional advantages, because when we have multiple machines which run the same database system, we can have a higher robustness, because even if a whole computer dies, you still have backup systems which have redundantly replicated the data. You have the option or the chance of getting higher performance due to parallelization and load balancing. This is a rather double-edged sword, so quite frequently performance does indeed not increase by adding more hardware. And especially for traditional databases, there will be a point where new hardware will actually make your system slower. So it's some conventional wisdom that for a traditional distributed database, that point will be around something like 100 machines, and after that it will just hinder the system, and that it's a really bad idea to add more than 100 machines to a database cluster. And if you need more performance, then you should do sharding, basically multiple database clusters running in parallel and each responsible for its own tasks. This is, of course, something which is rather annoying. Having a limit like 100 machines, that's something a big web page company like Google cannot do. I mean, Google is running, I think, 40,000 servers, 50,000 servers, I don't know, something like that. Ridiculous amounts. And doing now shards with 100 machines? No way. So that point will be one of the holy grails of new systems. So unlimited linear scaling, that for every machine you add to the cluster, performance also increased in a more or less linear fashion. Doesn't really happen for distributed databases. Still, you have the chance for higher performance, and it can become faster. Same should happen to storage capacity. If you add another hard drive, which is like 2 gigabytes, you should have 2 gigabyte, terabyte. Yeah, sorry. So if you add a new hard drive, your overall storage available should increase by the capacity you are adding. In reality, that also doesn't happen, so a lot of space goes to waste for maintenance and replication and other stuff, but at least in a certain way. Good. Of course, there are different types of distributed databases, and we can classify these things basically along the axis of their autonomy, so how autonomous is each node, and their heterogeneity, so basically how homogeneous or heterogeneous is the same system. This gets us to different setups, and basically the common setup you will start with is what I just call the regular distributed database. That's a homogeneous database system, and homogeneous here means that every node runs the same software. So for example, on each computer you have Oracle Data Manager or whatever, or DB2, in the same version. And this homogeneous software is connected via a rather strong network here, a local area network for single sites, and then multiple sites can be connected by a wide area network. And in that system, you have a globally shared schema. So basically all machines have the same schema, all machines can process the same queries, and now the trick here is how to execute queries in the most efficient manner. So homogeneous in the sense that you have the same systems running everywhere, and Good. Where does this setting come from? Well, that's a typical setting you will find in banking, for example. If you have branches, you have some as a headquarters, and the branches communicate with the headquarters and each other. And then if you have a wire transfer from one account to the other, and for example, Kreissparkasse did that for a long time. As you know, Kreissparkasse was a highly distributed bank, which until a couple of years ago didn't do any data sharing at all. So, for example, if you're a customer of Kreissparkasse, I don't know, Kaiserslautern, where I was as a student, and you move to Hanover, you can't get money from AC machines and from the bank branches because they will say, oh, but you're a customer in Kaiserslautern, we cannot access your account. That is not that long back. I mean, that's like 10 years until they solved that problem, right? Now, that's not a situation we want to have, because when you have multiple branches and my account is managed by one branch, there should be a wide area connection to the other branch. And now if I wire money from my account, which is done here, to one of your accounts, which might be here, there should be some way of transferring money from here to there. And that's basically the core problem you're dealing with in this setup. So how to distribute data there in the most efficient manner, how to distribute queries there in the most efficient manner. Then there's parallel distributed databases. Now, what does parallel mean? Parallel here means that all database management systems are homogeneous, so you're using the same software for each node, and that all the nodes are connected with very, very high speed, so super high speed connections. And each node is under full control by a central system. So each node, basically the nodes don't have any autonomy. When you compare that to here, we have these simple different sites. Each site basically is autonomous, can work by itself. If I cut these connections, it's still working somehow. Basically, this might be the bank branch in Braunschweig, that might be the bank branch in Hanover. If you cut the connection in Hanover, it will still work. You just cannot wire money to Braunschweig, right? And that connection is rather slow. We don't have that in the parallel setup. And the parallel setup, it's highly and tightly integrated. And that was one of the first architectures which became popular in the 60s. Basically, that was when first time we had mainframe clusters or grids. So basically, in a data center, you had highly integrated machine clusters where you could build a parallel database system. That type of stuff became extremely unpopular in the late 80s and 90s, and people claimed, okay, this is an old technology, nobody needs that, and basically let's go for one of the newer paradigms like sharding, which we will see later, and share nothing architectures. Basically they use commodity hardware. That's stupid doing that. And that was believed for quite a while. However, funnily, that right now becomes again one of the hottest technologies again. And people start digging out old research papers from the 70s, re-implementing stuff from that time. Why is that? Parallel databases are, for one, needed for multi-core computers. So with the rise of multi-core architectures, that has become more popular. And right now, there is a new development which is called NUMA architectures. I don't know if anybody heard about that. NUMA stands for Non-Uniform Memory Access. And these are parallel computer clusters where you have multiple CPUs and multiple machines, and you have high-speed network which is not going over some network protocol, which connects the main memory of different machines directly. So you have a cluster which has a shared main memory. And on a big computer cluster with shared main memory, you again can run a parallel database system. So it's again a very popular and hot topic right now. So these were homogeneous databases, so same database system and with some type of central control. Then of course you have heterogeneous database systems. Heterogeneous means that on the different nodes, on the different sites, you may run different types of hardware and software, of course. So you might have a DB2 database and an Oracle database and a MySQL database, and then somehow merge and mash that together into one system. And there is first, the simplest version of doing that is the so-called multi-database. Multi-database means you have multiple nodes which can be completely disconnected, and then you have a central server somehow, and people connect to the central server, states a query, and that query is distributed to all these nodes, and they give answers which get aggregated at the central again. And basically there is no integration nor shared schema. It's a very ad hoc setup. Why should anybody care about that? Well, that's a setup which quickly emerges by itself when you start collaborating. So for example, in research, or especially in biological and medical research, that was one of the central issues. And when you do bioinformatics, bioinformatics has several core pillars where it deals with. So one is something like gene alignment and ontology alignment and so on and so on. And one of the core pillars of bioinformatics is data integration. Data integration is exactly that. And the setup here was we have multiple research institutes working on some medicine, some cure for some illness. They all generate data. And now it's of course a clever idea to collaborate globally, so not everybody should work by themselves. And then some consortium rises, or the UN, or whoever claims like you guys collaborate. And now you just connect these databases, and of course they're not compatible. Everybody uses a different schema, everybody has different setup, different machines, different, everything is different. And then you end up with something like that, a multi-database. Very naive way of doing, of claiming having a distributed database system. That's of course pretty bad. The next step, when you spend some effort integrating this systems, is the so-called mediator database. Still, you have your distributed nodes. So this might be, let's say, the Helmholtz Centrum here in Braunschweig, which does some research. That might be another research center in, I don't know, Paris or whatever. And of course, nobody will ever change their systems, right? They don't have the resources of doing that. They don't, basically, they just don't want to do it. However, you would like to have a unified view on the different resources located at these different research institutions. Then you can build a mediator. A mediator tries to find commonalities between the data. So for example, if you have multiple research institutions working on the human genome, the probability is rather high that they ended up with a data model which is not too different. So likely it won't be the same data model, but as everybody is storing data about genomes, the probability is quite high that they do it in a more or less similar fashion. So what you can do is you can find similarities. You can somehow abstract from these things and do an in-between layer where you can translate between the individual schemas of the individual nodes and some kind of common schema. And if you continue with that path, you will end up with federated databases. The idea of federated databases is, even though you have nodes which are completely heterogeneous, which have their own schema, their own data, you still end up with a global schema where you can access all the data of the different nodes in a unified fashion. So this is, for example, something you try to do in bioinformatics, right? Bringing a global view on all the knowledge in medicine and biology. And it shouldn't matter where that data is stored and which institute actually created that data. And then somehow this federator has to figure out if there's a query for a certain genome, the genome X epsilon, whatever, where to get it, how to get it, and how to translate it into this common schema. And of course, generating this federated schema is a lot of work. So it takes tremendous effort for abstracting from the smaller schemas of the different nodes into a federated schema. So data,
Are there any heterogeneous databases which are not autonomous? Because I think all of the three are autonomous.
Yes. In theory, you could do that. We will be talking. So There was for a while this, for example, Java Enterprise Programming. I don't know if you ever saw that. So if you're a Java programmer, you will see that there's a Java Standard Edition and there's a Java Enterprise Edition. And I don't know, did you ever ask yourself what's behind that? So what's different between those two versions are? Not really. So Java Enterprise Edition was made to build middleware for big enterprises. And one of the core problems of middleware is, I mean, that's more or less the definition of middleware, is connecting the variety of different and probably heterogeneous systems you have in a big enterprise, in a big company, into one more or less centrally accessible infrastructure. And of course, this includes the problem with federated databases, right? And the big problem with federated databases is that you don't have direct control over the nodes. So basically, even if you do a federation here and you end up with a proper data mesh model, which, well, is federated, you still cannot run proper queries and proper transactions. So for example, for genome databases in research, it doesn't matter because genome databases are more or less read-only and it's rarely changed. And if something is changed, it's changed locally by the institution working with the data. So for example, if this is Helmholtz Zentrum here in Braunschweig, they will feed their database with new information. They don't care about the other nodes. However, if you now think of bank, and a big bank buys a smaller bank, and now they do a federated database. This is basically in industry how you end up with the federated systems, right? You do a merger, you buy a new company, you buy a smaller company, then you have the computer systems of the old company and the new company, you somehow have to integrate it, so you basically smash a federator on it and then you at least can access all data. The problem is if you now have two banks here and you want to wire transfer money from that an account handled here to an account handled there, you would need proper transaction processing, right? You should log data here, and you should log data there, then you should do your transaction, including all this annoying transaction handling and transaction processing in order to create asset transactions, right? That's not really possible in a federated database. And because this is very annoying, part of this enterprise framework programming was defining APIs and interfaces into database systems which allow a rudimentary access into the database core. And these interfaces have been implemented by the big manufacturers, so for example, DB2 and Oracle. They, for example, support Java Enterprise transactions. The result will be you have an application server, so for example like Oracle Glassfish or Geronimo or something like that. And did anybody do Java web programming? So stuff like Tomcat containers and these things? Okay, if you ever have to do that. If you do web programming in Java, which is very, very common in the industry, especially for middleware applications. I mean, that's not something you would do for your cool startup web page, but for folks who are not whatever, they do a lot of Java Enterprise programming. So if you do a web application in Java, you basically have this web container. It's the so-called war container, which you deploy to a container server. Now, the most famous container server is probably Apache Tomcat, which is an open source project which has been around for basically, well, forever, which is a system which can deploy these Java archives to a web interface. And yeah, then you have application servers. And application servers are like these container servers, just significantly larger. That's something like JBoss, for example, Geronimo, Glassfish. Right? And these servers are extremely heavyweight and big. And why is that? What do they do? One thing is a lot of enterprise features like messaging, but another part is Java transactions, the database transactions. One thing you can do in a Glassfish server, which you get automatically when you download Java Enterprise Edition from Oracle, then you can connect to that middleware server multiple databases. And if these databases support this open transaction protocol, then the enterprise server can directly control how transaction and data management and queries are handled in the database core. And then you will end up in a federated setting with something which looks like this, right? It's a simulation of this regular distributed database. It's not as powerful, it's not as good, but it goes strongly into that direction. So you still have a heterogeneous system, and by power of standardization, you force it to behave like a proper homogeneous database. That's also one of the reasons why Oracle bought Sun and Java. So a lot of people wondered why the heck is Oracle buying Java. Yeah, that's one of the central reasons. Because they wanted to do that properly, because they wanted to get a stronger standing in the enterprise programming community, and having that middleware infrastructure and having these standards for transactions helped a lot. So it was a very clever move from Oracle buying Sun Technologies and Java Systems, because it's really a good match because of all these features. Did that help or answer the question somehow? Okay. Good. Why should you need these things? Well, obviously, we talked about that quite a bit. For example, medical research or research in general. Research in general, you end up quite frequently with federated databases, with mediator databases, or these really bad multi-databases. So they just merge together very heterogeneous systems, but want to allow everybody to access your results. And that first came off in astronomy and these things, where you had these large files which needed to be accessed. So, for example, telescope data is multiple terabytes each, which in the time when this was a problem, like in the 80s, really a lot of data. I mean, nowadays it just fits on a hard drive, so then it didn't. And a friend of mine, actually I wanted to update that, somehow I forgot to do it. So a friend of mine, he works at CERN. You all know CERN, I guess, in Switzerland. We're doing this Large Hadron Collider experiments. And he's at the data center of CERN, and they are probably one of the largest distributed database systems in existence. Because their Stupid Hadron Collider creates, I don't know, several terabytes of data per hour or something like that, so it's really ridiculous. And somehow all this data needs to be stored. And it's the same, which here is this astronomical information applies to that too. So basically the data is dynamic. It changes quickly. So per hour you have multiple terabytes of data going into the system and needs to be stored. It has very, very different multiple data types. So you have primary data from the sensors. You have analysis data from spectrum analysis, from computational models. You have written text. You have journals. You have catalogs. So all kind of stuff which all goes here. And what is very important, or has become important for the scientific community, is data provenance. Data provenance is something which is not really covered by traditional database design. So provenance means for all data you access, you need to be able to track down where this data comes from, right? You have to show how the data was transferred and how it ended up with you. This is very important to show that it's indeed valid, that it's reliable, that it comes from a proper source. And data provenance it's a big problem also for the traditional database community now, because a lot of new laws force companies into providing data provenance. So for example, a couple of years ago, the United States made a new law that companies have to keep untampered records of all transactions for, I think, 10 years, and for everything have to prove how it was processed and where it came from. And that's super annoying. And basically the only way of doing that is doing heavy versioning. Right? So they have a huge collection of write-only media where you just don't change data, but just create new version of data all the time and never throw something away. This is our Sorbonne-Oxley Act, Sorbonne-Oxley Act or whatever, I think something like that, which created a lot of problems for companies. I mean, in research, that's also very important that you can always go back in time. So basically think about it like a big code repository, where you can always check out the older versions of the code, and for old code can see who modified what and when. Something like the version or Git perfectly supports these requirements, right? You can see in a Git repository every change and every modification to the code. That's pretty good provenance. So think about it like bringing Git features to databases. Good. So for example, for NASA, they have highly distributed systems by branch, so solar systems research, sun systems research, university exploration research, which is then, so basically these branches have a shared and common schema, but then it's mediated together, so in the end they have some kind of mediated database where you have limited search capabilities up front, so basically these nodes are more or less independent than aggregated. Non-surprisingly, one of the big players which pushed a lot of developments in that field, they are military. That's something people don't like in Germany, but on a global scale, a lot of technology we use in our civilian lives are actually funded by diverse military research agencies all over the world, especially DARPA in the United States is pushing a lot of money there because military is very, very, very interested in having proper distributed data handling. So basically, that type of research goes also back for decades now. And here we want to consolidate all type of different data, like sensor data, geographic data, technical information, movement of troops, whatever, into one big combined command screen, which from a technological point of view is extremely difficult. And of course, as it's the military, it should be extremely fail-safe and it should be rather resistant to modification or attack. So by just removing certain nodes, the system shouldn't crash. So non-surprisingly, they spend a lot of effort into robust system design. And a lot of stuff you find now in cloud storage systems, which claim to be disaster-proof or tamper-proof, were, actually developed techniques for military applications. Good. What are the hard requirements you have here? Well, it should be consistent and up to date all the time. It should be distributed. It should be very resistant to change, to failure, and highly fault tolerant, and it has a lot of real-time requirements. Pretty hard to do. And there are some examples. I think I have to a little bit to speed up here for different things. Good. I think we will do a break in 10 minutes. I'm just covering transparency, and then we come to the other topics. Good. Furthermore, we have heterogeneous, how heterogeneous a database is. We have how autonomous nodes are. Another thing you can do is how transparent the database is. Then we have basically three types of transparency, which are schema transparency, query transparency, and update transparency. And this is basically the amount of control and knowledge a user has to put into the system in order to make it do something. So for example, schema transparency means, do I as a user have to care how data is distributed? In some databases I have to do that, so there are manually distributed data myself, which might be an advantage. So as a system designer, I may take some of my domain knowledge and use it for doing a better distribution. However, that's also a lot of work and, rather annoying work. So for a lot of use cases, it's better when it's fully transparent, basically, when the system distributes data itself, maybe by load balancing or completely autonomously. And the simplest way of doing a data distribution is probably hashing. You just hash data in a hash ring, and then you distribute it to the machines according to whatever hash you just completed. This is, for example, like peer-to-peer systems. In peer-to-peer systems, you have full schema transparency. You don't care whatsoever where your data goes, and nobody actually even knows where the data goes. The system will handle that. It's not your problem. Same goes for query transparency. If you do query, do you know where data is? Or do you have to ask the system before? Do you have to care? Yeah, also there are some systems you need to know where data is stored, for others you don't. And usually the less you need to know, the simpler the system is to use. And the same also applies for update transparency. Do you have to specify every time where data should be replicated and in what degree? Good. Of course, all these things have advantages and disadvantages. If you have full schema transparency, basically if you have to deal with distributing your data yourself, the problem when it goes, so the advantage when it is done by the system automatically is that of course you don't have to do any considerations about it, you can just let the system work. However, the disadvantage is that often you do not use semantic knowledge. For a lot of systems that's not really a problem. So a lot of these peer-to-peer systems, really large systems, they just claim, okay, kill it with iron, when it's too slow, we just add more hardware and then it will be fine. However, for actually really optimizing a system, some manual control is often quite beneficial. So schema transparency can be helpful or can be harmful depending on the use case. Same applies to query transparency. If you have full query transparency, then of course you need a proper distributed query optimizer who is able to do a proper distributed query, right? And that's not easy to do. So a simpler system will go with no query transparency, and you as a user have to do the resolution yourself. That will be the topic of the next lecture, I guess. Good. Update transparency, that's basically where stuff goes and how to deal with transactions. It will be topic of week 3. That's basically the problem of, how to do transaction. Advantage of that is, of course, everything gets easier. Disadvantage, it takes a lot of effort. So update transparency is a very, well, powerful but expensive feature. Good. So what will we do with distributed databases? Next lecture will be partitioning and sharding. So basically deciding where your data goes. That's the schema transparency part. Third lecture will be about load balancing, fail safety, and query processing. So how to retrieve your data. Now this is where to store your data. This is how to retrieve your data, how to do query processing and query optimization. Number 4 will be transaction processing in a distributed environment. After that, we are done with distributed databases, right? It will only be 3 weeks, and then we will move to different topics. Why that? One of the things we will learn in the next 3 weeks is that distributed data systems have a lot of very cool features, which are very useful and powerful, but all these features come at a very high cost. And one of the costs, I mean, most of the things I already mentioned, is that these systems don't scale well. Not beyond 50 to 100 nodes, you don't get a proper performance increase. You don't want to do that. You want to have linear scaling. If I use 10 times the computers, I want to have 10 times performance, right? That I cannot do with a distributed database, but I can do that to a certain extent with a peer-to-peer system or cloud system. Therefore, we are moving there. They have very limited flexibility with distributed databases. So the administrative overhead is extremely high. Adding a new machine to a cluster is a lot of work. Changing something with a schema is pretty annoying. Now, so you need a lot of manual work and maintenance in a traditional distributed database. We want to do that differently, and that's what often is called elastic computing. Elastic computing means you can just throw in any hardware you want, and the system will just cannibalize it and use it however it sees fit. So you don't have to care how to proper tune your system, how to use the hardware properly. The system will know how to do that. That's something that we want to move to. We will do that with peer-to-peer systems and cloud systems. Also, traditional databases have extremely high hardware costs because databases work best when they get specialized high-grade hardware. Now, so for usually when you have an EB2 cluster or Oracle cluster, it runs on these big enterprise machines where you have redundant power supply and redundant hard drives and redundant whatsoever, and you have special high performance networking. Maybe you have even something like storage area networks or this NUMA direct memory access things. That's all technologies which are very good but super expensive, right? And if you want to scale to something like 100,000 servers or a couple of million servers, like for example Google does it, it won't work with high cost Dell hardware or IBM hardware. You want to use really cheap crap hardware. And one of the first innovations Google did in 2001 is claiming, okay, we don't buy our hardware at Dell, but we buy it at the flea market. And yeah, then we have very cheap data centers, which of course is true. However, it introduces a lot of new interesting problems. Good. Of course, we can all do that. We can build systems which can scale unlimitedly. We can do systems which run on cheap hardware. We can do systems which have higher performance, but that requires new design paradigms, it requires changes to the architectures, and it requires that we sacrifice some features. And that's what we will do with peer-to-peer systems. So we have unlimited scaling, we have flexible schemas, and we want to introduce this elastic computing, right? So these are the next two topics, peer-to-peer systems. There, in peer-to-peer, you have this idea to store everything decentrally on the worst hardware you can get, basically your home computers in your student dormitories or something. That doesn't necessarily mean that the computers are bad, but it means the connections to your computers is bad, so that you can just switch them off whenever you feel like it. So basically, it's a really horrible network. So the first prototypes of peer-to-peer systems were developed at universities, for universities, on computers which went on and off all the time, which had bad connectivity, which had bad hardware, which were connected via stuff like ICM or modems or stuff like that, so really bad. And still you want to build a flexible, scalable system. From the lessons learned we get from peer-to-peer, we move to cloud systems, which is basically the exactly same thing, like peer-to-peer systems with traditional database features thrown in, and now under the control of a single company and data center. But still, it's an amalgamation between databases and peer-to-peer systems in the company. Good. I would say we do a short break of like, I don't know, 10 minutes. Das ist ja egal. Wir müssen uns ein bisschen beeilen. Ich habe zu viel rumgelabert am Anfang. Good. Okay. Yeah, let's just slowly move to this distributed peer-to-peer system. I just mentioned this fact with hardware costs. So what does it actually mean? Here I have some, all the numbers. I actually want to update it, but you get the picture, I guess. So if you want to buy typical, data center style, industry style hardware, let's say some Dell PowerEdge servers, you have actually to pay quite a lot of money. Now, so for example, if you buy this PowerEdge M19 systems here in 2011 for 83,000 euro, you get 384 gigabyte of RAM, 3 terabyte of RAID, so probably nowadays it's something like 10 or 12, and a big Xeon processor with a lot of cores and quite a lot of computational power. So basically, if you build a whole rack, so one of these here big rack storage spaces, put in these blade servers. In case you don't know what blade servers are these tiny little things here, which are very compact servers, which you can stack very easily next to each other. So this is one blade server, 1, 2, 3, 4, 5, 6, 7. They form, a blade rack, which is like 12 machines usually. Then you can stack these things over each other, and then you have something like 100 something servers in one single rack, right? That looks rather good. And for $1 million or so, you get 512 cores, 12 terabyte of RAM, and around 100 terabyte of hard drive. Plus additional costs for yeah, basically the rack itself, climate control, and all these things. So you get quite a lot of stuff for extreme amount of money. And there is this analogy that when you do it like that, that's like your data and systems living in these high-class condos with beach and, you know, view over the city, which is good. I mean, that's something a lot of companies do, right? That's the typical state of the art in a company, industry, server operating system center. However, what you could also do is here what Google did in 2005. So Google is very secretive about what they do. They don't tell a lot. But from time to time, they publish one of their server technologies, and that's basically in 2005. They had servers which looked like that, right? That's the main board, glued to cardboard paper, and then put into some fiber proxy, well, something which looks like a rack, without any housings and free running cables, and it's really horrible, right? And if you do it like that, I mean, it's hard to say because Google back then bought used hardware which was not used anymore by other companies. But even if you go for new hardware, let's say a desktop system in the same time, let's say also from Dell, why not? And you get a desktop system for €1,000 each. In the end, for the same 1.2 million, you get 9,600 cores, 20 terabyte of RAM, and 2.5 petabyte of hard drive. Compare that to the Blade server, you get for the same money significantly less hardware. Okay, so it might be a very good idea to use actually these desktop machines, so 120 of them or 1,000 of them, instead of this really cool server. However, the problem is, if you do that, you run into a lot of problems. And we will have a detour about that, I think, in lecture 11, where Google has failure statistics on their hardware servers. And they have something like one hard drive failing, I think, every 3 or 5 minutes. So basically, if the hard drive fails in one of these machines, the machine is broken and cannot do anything until it's fixed. And they have a guy running around in the operating center with one of the shopping carts, and he's doing nothing else the whole day but changing hard drives. You just go somewhere, there's a little ticker like, oh, broken hard drive over there, goes there, replaces it, goes there, replaces the next hard drive. That's all this guy does, right? And your software has to keep up with that. And here in that system, now, failure rates are significantly lower because here you have redundant data, you have redundant hard drive, you have RAID drives and all these things. So all this new technology which prevents that stuff breaks that easily. Good. Now, with that in mind, how can we build software which can run on this really shitty hardware which breaks all the time? And we can now learn a lot from peer-to-peer systems. We talked about that quite a lot already. Peer-to-peer systems became extremely popular, especially in the end of the 90s, so 1999, especially with Napster, when it came into the media all the time. And the idea in peer-to-peer systems is that you have a large number of peers, yeah, you have 1,000 or 500,000 computers because you get it cheap to buy a proper server, which may join and leave all the time. Well, for file sharing, it's people switching on their computer and off their computer all the time. For our setting, it's computers breaking all the time, right? So leaving and joining. And you only have very rudimentary features you can do and which you do need, right? Because a lot of these systems were developed for either file sharing, which is super simple. In file sharing, we just need to find the file and then transfer the file. That's rather straightforward. Also, the data model behind file sharing is very simple. Right? You have the file, which is described by its file name. Maybe you have some metadata, like, I don't know, actors in the movie or when the movie was released or some short description. But even that is not supported by most systems. The most successful file sharing systems in the end just supported hashing, usually hashing by name, right? And that's as simple as it gets. And interestingly, that very simple feature set is also enough for a lot of business applications in companies. So yeah, if you only need very simple features, peer-to-peer systems is a very good solution. What is a peer-to-peer network? A peer-to-peer network is a virtual overlay over a real network. So basically the idea is you have a real network, let's say the internet, and in the internet you form a virtual subset which forms a new network over an existing network. And usually you do that because those people joining the peer-to-peer network have some common agenda. That common agenda might be, well, pirating movies or music, but it might also be doing voice over IP calls, like Skype, for example. Skype is also a peer-to-peer network. Well, a very simple one, but still. It might be sharing of resources. It might be doing, so one very hot topic right now, again, used to be a hot topic like 10 years ago, but now again it's rather popular, is distributed search. So for example, they have tried to build search engines which do not rely on a central organization like Google, which is in leash with NSA, as everybody knows, but they run it, in a democratic environment over all users of the internet, or at least that's what the advertisements claim. So basically, you have a group of people with a common agenda which form an own network. And within that network, they form own connections. So you can have an own network topology on top of the internet. So while the internet topology might look something like that, you now do an overlay network which has a different network structure. Still, all messages which go from here to here in the overlay, these two computers are directly adjacent, so they are neighbors. But that's just a virtual neighborhood. Still, if you want to communicate from here to here, you have to locate that computer here in the IP network and then ship the message to the proper computer. That's basically the idea of a peer-to-peer network. A network topology on top of an existing network topology. What are the challenges here? Well, first challenge, of course, how do you organize that network? How do people join that network? And if they join, well, how do you build this network topology in the peer-to-peer network? Then, if you have that network and you just saying, like, okay, let's do a ring here with some interlinks. What was I saying? Okay, so if you decided on a topology and you joined these nodes, how do you find anything here, right? Because usually, remember when I was talking about transparency, you need to know where data is stored. You need to know how to distribute data. For peer-to-peer networks, and we just stay with the file sharing case, it means that when you join a peer-to-peer network specialized on piracy, for example, you bring your own content, right? And nobody knows what that content is, but you, right? You have some movies you got from somewhere, you join the network, somebody else wants to download these movies from you. How can other people find that? How can they access these resources? So somehow you need a central repository, a central catalog, or some clever technique of routing queries in such a way that your new data can be found. And of course, the same problem applies when you try to build a peer-to-peer system in a commercial environment like Amazon Dynamo. Same problem. Good. So discovering resources and then transferring data and transferring, well, queries. Good. We will cover all these issues in weeks 5 to, well, I think 9. So basically we do peer-to-peer, pure peer-to-peer for 4 weeks. Then we will do 1 week of how to transition from peer-to-peer to cloud storage, and then some cloud storage after. So, I think we can skip that. I mean, why did peer-to-peer become successful, and why in the 90s? Basically, that's because that was a time when people actually had proper computers and proper internet. And it's no accident that the invention of DSL and internet flat rates coincided with the rise of popularity of file sharing. Surprise. Anyway, good. With the rise of better computer and better internet connectivity, you of course did also have peer-to-peer systems, and which relied on sharing resources between peers, which could be information, so files and documents, like in the classic use case of file sharing, which can be bandwidth, which is, for example, for load balancing systems. So quite a lot of web hosting systems are actually peer-to-peer systems where you do load balancing between multiple web servers. It can be storage. So there are a lot of storage engines running on peer-to-peer technology, especially cloud storage systems do that, or it could be computing power. So especially in scientific computing and grid computing, peer-to-peer systems are very, very popular still. And we will cover that also in, I think, lecture 12, when it comes to MapReduce computing, which is one of the typical computing paradigms for big data processing. Right? You have a lot of computers, each computer stores data, now you have to process it somehow. Good. Yeah, let's have a short detour into the file sharing application, because it's a big historic impact it has on a lot of things. Basically, file sharing is the application which makes peer-to-peer technology viable, developed a lot of technique, and is also one of the applications which formed a lot of, well, the rights infrastructure and a lot of the laws we use today. And basically, it all started out with Napster. I don't know if you know the Napster story. Usually that thing intended to go rather differently. So Napster was invented in 1999 by two students who got bored from sitting around and listening to the same music all the time. So they built a music sharing network for their dormitory, which worked out rather nicely. So that was a time that people still bought CDs and then ripped them to their hard drives, which took something like 7 hours. So it was very annoying ripping CDs yourself. And after you had the MP3s and all your non-nerd friends laughed about you, what a stupid idea to listen to music via computer, you could share it with other people which were like-minded. That's what Napster was about. And funny thing is, being the United States, being Silicon Valley, being the big internet bubble, of course after that system worked, the inventors of Napster tried to commercialize it and make a proper product out of it. And they had this really ridiculous, stupid idea of selling music in the internet. And they proposed that idea to the big music labels, and they are just like, you guys, don't be ridiculous, that's the most stupid idea ever. People will buy CDs, forever, all into the future, and when they don't buy CDs, we build a new thing which looks like CDs. So that's stupid, go home. Yeah, they tried that a couple of times with basically all major labels, and after nobody thought that the idea of selling music in the internet was a good one. They basically just published their software, and you know what happened? Basically, people got now their music from the internet. They just didn't pay for it because, by that internet piracy, peer-to-peer piracy was born. Of course, there was piracy before that in newsgroup and stuff, but Napster made it public to everybody, and surprisingly, people loved getting music from the internet just because nobody could buy it. Well, yeah. And it took another 7 years until this buying from the internet thing became somehow popular with the music industry. Probably because of Napster and these things. And now what happened there in this Napster, it's very interesting from a legal perspective as well from a technological perspective. I don't know if you still remember these things or if you were too young for that, I don't know. Napster got insanely popular. And they got sued very, very quickly. Back then there weren't any proper laws for internet piracy because that was a new thing. But after a while they shut Napster down. Why did that work? Well, Napster was a centralized peer-to-peer system. You had a central server, you had the peers, and all these problems I was talking about, like topology, how to find stuff, how to do queries, were handled centrally. So you as a new peer would connect to the central server, give a short list of all content you have available to the central server, and it then would distribute the queries, and the central server knew everything which was going on. Basically, by killing the central server, the system was shut down. And internet piracy was dead, at least for a couple of minutes. Because what happened next is people built a system which cannot shut down by killing the central server, either by hardware failure or by legal interdiction. And that was the birth of Knutella. Knutella is a system which was designed with the single purpose of never ever being able to shut down whatever you do. And basically they did that by massive distribution, and that was the idea of preventing a legal crackdown like happened to Napster in the future and make piracy basically robust against any kind of interdiction. Did not really work out that well because Nutella had a lot of different problems, and you could sabotage the network, which happened quite frequently. You could flood it, you could spam it, you could do denial of service attacks. So it didn't work out really well, which led to the next system, which was Kazaa, which made a more robust technology, which was better suited to fight off simple attacks, which also didn't work out too well, which led to the development of new technologies, which were more robust. You see what happens. So it's kind of an arms race. And the result of that is that basically the pinnacle of peer-to-peer technologies in the end was distributed hash tables. Distributed hash tables were very robust systems which could scale extremely well, which were real robust against node failure, against attacks, against spamming, against basically everything you could reliably throw at network, and at the same time supported a lot of cool features. So basically best piracy software ever, which then later was developed into the seed of cloud technology. So isn't that nice? So basically the legal race with area helped us to develop new software. Also, of course, you have a lot of also legal applications for peer-to-peer software. So in the early ages, like 2006-07, before you had this really massive cloud infrastructures we have nowadays, a lot of peer-to-peer systems like BitTorrent were used to distribute large files, also legal files. And a typical example here is World of Warcraft. I guess everybody knows that. It used to be the most popular MMO ever. So now easily surpassed by all these stupid mobile games. But anyway, they had this problem that they had patches, which were rather large at the time. So something like 1 gigabyte or 2 gigabytes or 5 gigabytes, which nowadays is all laughable. But 2008, that was a problem. Getting a gigabyte patch to 12 million users at a given day. How to do that? The Sintra server doesn't work. I mean, it will just crash. So you need a proper, clever way of doing it distributedly. And they use BitTorrent for that. BitTorrent is not really a peer-to-peer network per se, but it's a peer-to-peer content delivery technique. We will cover BitTorrent, I think, in lecture 6 or 7. So basically, BitTorrent does not address the problem of topology and how to find stuff. It just deals with the problem, if you find the stuff, how to transfer it as fast as possibly using a distributed setting. So that worked out wonderfully for World of Warcraft, for example, which was very annoying for all these people in 2008 who had an internet provider blocking BitTorrent because that's all piracy, because they also couldn't play World of Warcraft probably at that time. Very sad. Anyway, good. We can hop over that. Also, Skype, in case you didn't know, is also a peer-to-peer system. It uses peer-to-peer technology to route calls through firewalls. So if you ever wondered why you can call people via Skype, even if you're in a corporate firewall, that's because they use this peer-to-peer unicast technology. Where from a central server, you just initiate the connection, so a little bit like Napster. So it's a technology very close to Napster. And instead of doing a file transfer at the end, you just transfer the phone call. And you route the phone call over multiple nodes. So it's also peer-to-peer applications. So for historical reason, that's a cool diagram you might have a look at home because you probably can't read it here. But basically what it does say, what it says is the hot years of peer-to-peer were from 99, invention of Napster, to 2008. Basically 2008 was the year where stuff like iTunes and Amazon digital distribution systems became popular, and people didn't need to pirate stuff because you could buy it, or you could go to Mega Upload, which is also now gone. And you had stuff like YouTube. So basically people found a lot of stuff they could do beside internet piracy to get entertained. But what you could see here is, you start here, this is 99, this is 2000, this is 2010. that this is the distribution of traffic in the internet. And it started out in the beginning, so 99, basically that's all FTP traffic, right? Binary file transfer. Used to be very popular 20 years ago. That becomes less and less and less, and this big red one here is web traffic. Because, I mean, the web was just invented, I think, 1991 or something, became super popular in 99, and this is like the peak times of the web, which is something like 2002, 2003. And here, that's peer-to-peer, right? And here, at this point of time, peer-to-peer took around 70% of all internet traffic, which, of course, was something very annoying to a lot of internet providers. And nowadays that's going away, so now we have the major part is this one here. If this diagram would go on, it would indeed, go like that. And now this purple part here is, I think, 80% or 90% of the internet, and that purple part is internet stream video, so stuff like YouTube, Netflix, and so on. Interestingly, what's happening in the data centers of YouTube and Netflix is not too different from what we are doing in this lecture. Basically, these things are content provisioning networks, and content provisioning networks are just specialized, huge peer-to-peer systems which are run by a company with proper hardware instead of run by, well, community users. Good, that's basically protocols. I think you can look at that at home when you're interested. So, one interesting thing is, you might see, that's this one here, Fast Track and BitTorrent. This is how quickly technology can change. So basically what you can see is, here that's Knutella, which stopped working in 2003 because it had too many weaknesses, and stuff like eDonkey became insanely popular, especially fast, and after BitTorrent was invented, BitTorrent took over basically all file sharing in a couple of weeks. That's the only thing you can see there, interestingly. Good. This is what you actually did in file transfer. You can look at that. Good. Internet piracy and peer-to-peer system. Why does that help us? That brings us to cloud storage. What we want to do in cloud storage is building systems which can cope with the demand of internet companies. And for them, traditional database technology was too expensive, too inflexible. It provided many features they didn't need, and they needed a significantly higher amount of storage and performance. And the big drivers behind a lot of the cool internet technology we have nowadays are unsurprisingly Google. Yeah, Google would have thought. They are Yahoo. Yeah, Yahoo is one of the companies which don't get taken seriously anymore because, yeah, they don't do a lot in the last years. But Yahoo are one of the big pioneers of internet technology. They did a massive amount of work back then, and they also shared a lot of that work. Then we have stuff like eBay, who's also one of the old web companies who did a lot of work, but they were not very sharing, so they kept a lot of stuff themselves. And something not known by a lot is it's Amazon. Amazon was always a company which tried to drive internet technology really hard and share it with people, well, basically in exchange for money, but still they shared it. So Amazon is one of the companies who developed a lot of technology behind nowadays internet stuff. This includes a lot of cloud storage systems, or the first commercial cloud storage system they are offered by Amazon. That includes internet services and service-oriented architectures. So basically that idea that you have a loose coupling of software components which just do communication via some web service calls, to nowadays stuff like question answering. So it's one of the big companies driving a lot of research. And Google, of course. Good. So what do we want to do? We want to combine the ideas from peer-to-peer and file sharing with ideas and techniques from distributed databases. And by doing that, we want to do highly scalable data centers which offer a lot of cool features like being elastic. It means you can add any hardware and without any hassle. than having near linear scaling, so every hardware you add something. You want to have flexible data schemas, you want to have high fault tolerance, you want to have unified interfaces, so you're not dealing with special interfaces, and you want to use cheap and crappy hardware. Now that's what you might be able to see on that picture. Basically what you see here, these are simple desktop PCs, probably bought used, which were just put into cheap storage racks and connected to each other. So it's basically a cluster made out of old office hardware, which is indeed how Google built their servers in the beginning. Good, that's one thing. That is, when you're Google, when you're Amazon, how to organize your data center. However, there's a second problem, because cloud storage is not only about technology. I mean, the label cloud was applied to basically everything between 2009 and 2013. So it was one of these hype topics, and if you claimed you're an expert in the cloud, then you got a job immediately. But it's unclear what cloud actually means. Of course, for one, it means that. This is cloud storage. It means this flexible way of storing information in the fashion as described here. Cloud also means computation in a distributed fashion. That covers stuff like map and reduce and distributed computation. But these are also technological point of views. What cloud also entails for a lot of people is a certain type of lifestyle and or business model. So for a lot of people, cloud means that it's just done someplace else and you don't care, right? So one of the early cloud offerings by Deutsche Telekom, for example, which pushed into markets with a lot of television advertisements for their cloud storage, was actually not cloud technology at all, right? What they just did is they provided you a file upload to a central server. That was not cloud. But it was cloud in the sense that you don't store the stuff on your computer, but you move it somehow to telecom and you don't care what happens there. It's a change in usage. And that's a very, very important part of this omnious cloud topic. And basically it is you buy or rent a service with another service provider or company, let's say like Amazon, like Google, or like Telecom, and they take care of your problem. And you pay for it. Either you pay for it by money or by personal information or by customer binding and then buying other products of that company, but somehow you pay for it and they take care of it. And that has a lot of interesting applications. And as I said, one of the first players on that field is Amazon. And why is Amazon the first player on that field? Actually, that makes a lot of sense, because Amazon was the first globally distributed general store there was, right? So they're selling everything, everywhere on the world, basically. And one of the core problems Amazon used to have was that customer behavior is not uniform. So it's not, so people are not buying stuff at a uniform distribution, but there will be peaks. So for example, before Christmas, everybody needs Christmas presents. Or in the United States, it's Black Friday. So that's the most feared day in e-commerce, because at Black Friday, everybody goes shopping. And in order to handle that, you have to have a lot of computational power in order to handle these peaks. And this has a lot to do with linear scaling and elasticity. Now, if you have enough hardware power to handle these peaks, what do you do with all your stuff when you're not in a peak, right? What do you do on Wednesday nights, in summer when everybody is on holiday? Are your computer idling? Nah, could be bad. So basically the idea Amazon had is they built this cool cloud infrastructure for themselves, something like that, to use for their own product. But then they had this brilliant idea, like, okay, now these systems are idling around, they don't do anything, why don't we rent it out? And that's basically the birth of cloud as, well, the business model. They rented their hardware they didn't use, and everybody could use their hardware and pay Amazon for it. And that now became an own business, so Amazon is making a ridiculous amount of money for renting out server hardware. And that is very, very important for a lot of smaller companies. So imagine you're a small startup company and you build a big product nobody cares about. You have 5 users or 10 users, and you just got funding, you know, by some kind of startup, hedge fund, whatever thingy, and you got $1 million and nobody cares still about your product. And then some newspaper publishes, oh my God, this guy makes this really stupid application which doesn't do anything, but it's so insanely cool. And then everybody in the internet needs to try it. And these things rise in popularity insanely fast. So that is a very common thing with a lot of new applications, that they become popular in the matter of days. And when they are lucky, they stay popular. And when they are not lucky, nobody cares about them in, well, 2 or 3 months. Right? So now the cycles of popularity for products are extremely short. Now, what do you do as a small startup? You're 3 people, you have a couple of million euros. Do you buy hardware to actually, well, cover this tremendous influx of users? And if yes, how much of it? And this is usually called the Reddit effect. The Reddit effect is, I guess you know Reddit. This is one of the big community bookmarking pages where a large number of internet users discuss about what is popular and hot right now by linking to pages. As soon as something enters the Reddit main page, millions and millions of users will click on it and will go there. And small companies, they will just break behind that. So this is a very common thing that at least around 2010, around 2011, you bring a new product to the market and it crashes first day because it's featured on Reddit and it dies. So one example here is Facebook, which grew significantly slower, but still very, very fast. I'm going to skip over that. And my favorite is that one because it was just so ridiculous. I mean, on the current perspective, that's still, yeah, pretty lame. But Farmville in 2010 was one of the first applications which grew in popularity within days. So within a couple of days, Farmville was able to amass something like 150 million users out of nothing. And I don't know if anybody of you played Farmville or has actually seen Farmville in the last years. I mean, all that Farmville magic maybe, well, stayed there for a year or so. So it became popular in days and then disappeared, well, over the course of a year or 2. So it stayed surprisingly long. But the growth was tremendous. And the problem with Farmville, for example, was that it reads quite a lot, but it also writes a lot, which is a large challenge for data management systems. So usually a lot of reads is fine as long as you don't write. Remember back, discussion about redundancy, and if redundancy is good or bad. Problem with redundancy is that you get into problems when you want to write stuff, right? Or these write and anomalies and update anomalies. However, with high redundancy, you can increase the read performance. So if your data doesn't change, having high redundancy is a very good thing because you can speed up reads very, very well. So usually you want to have a ratio like 20:1, so 20 reads per 1 single write. Having a ratio like 3:2 is pretty bad because it means you have to write a lot, which brings you into redundancy problems. So how do you do that? How do you deal with that? How can a company like Züngner and back in that time deal with such spikes? Yeah, by basically renting in the infrastructure hosted by Amazon or hosted by Facebook. So they don't do it themselves. They just use the massive experience from Amazon and pay them for that. And that's also a very, very important part of the cloud label. Not only technology, but also the business model. Good. Another small detour is about Google servers. Google doesn't say and tell a lot about how they do things, but in 2007 and 2009, they published 2 white papers, which are now already 8 or 6 years old, but still, it shows an interesting picture, and yeah, nobody really knows what Google is doing nowadays, but back then it was very interesting. Because in 2007, they were the 4th largest server producer on the world, which is rather surprising because you cannot buy Google servers anywhere. Basically, they produce these servers just for themselves. And they had over 1 million servers and 34 data centers. Now it's significantly more than that. So how does that work? How did they do that? Basically, one thing also a lot of people don't know is that Google owns a massive amount of the fiber cables on the world, right? Because they have all these data centers, and these data centers generate a lot of traffic. Basically, at its core, and we just stay with Google Web Search. So Google Web Search was their first product, and that was the one driving a lot of innovations. Web Search works in a very simplified fashion like that you do a local copy of the internet, which is a very weird idea by itself. So you crawl the internet through a local copy, somehow in a compressed format, and then on that copy, the index, you compute a lot of statistics. So most popular among it is the PageRank, which is a rather expensive computation where you analyze links going into web pages and going out of web pages. Basically, what happens is now they have their web index distributed over all these data centers and computing this massive PageRank continuously all the time. And for doing that, they have to shift traffic over between their data centers all the time. So basically, they create a massive amount of traffic, something like 7 to 10% of all internet traffic is just internal Google traffic, just Google communicating with itself. And therefore, they have to pay ISPs for that. So they have to pay a lot of money to internet service providers to actually transport their traffic. And as that was very annoying, they built their own cables. And they actually do own deep sea cables connecting Asia to America and America to Europe and so on. And in 2010, 60% of these 7% of all internet traffic was routed via their own internet infrastructure. Now this percentage is significantly higher because they expanded on that. So Google, if they were an ISP, they would be probably among the third largest or second largest, nobody really knows, but they would be a pretty large internet service provider. Good. So these data centers are extremely expensive and use massive amount of energies. I don't know if you followed these issues. So right now there are a lot of discussions how to build efficient computing centers, like using containers or moving them to Antarctica or, doing all kind of interesting hacks, how to do that in a better way. And the core problems here is definitely power usage, because computers use tons of power. And when you use a lot of power, you're also producing a lot of heat. So basically, the core problems is getting rid of the heat and producing the electricity. Now, so for example, one of the largest computing centers Google hosts uses around half the amount of energy than the whole city of Braunschweig, including all industry and all people living here. So it's really tremendous effort which has to go into computational centers. Good, but how do you actually build these things? Google has one of these weird ideas which now become very popular, so this has become more or less state of the art, to use extremely cheap and bad and outdated hardware in a very flexible fashion. So in 2008 they published this white paper where they claimed that they use old desktop commodity hardware which they buy for very, very cheap because it got thrown out of other companies, took these things, replaced all the power supplies and replaced them by smaller batteries, and these batteries get into a central power supply. Good. Now you just take these computers, glue them to cardboard, put them into a big cheap rack, and from these cheap racks you put like 15 of them into a standard shipping container. These are the normal containers you can find on shipping ships or railways, and it's a shipping container. And in the shipping container you have an own power distribution system, you have an own climate control, and you can just take a stapler and put these containers on top of each other, move them to a different data center, and basically the only thing which goes in and out of this container is a huge cable for power and a huge cable for internet and a big thing for climate control, so with fresh air and exhaust air. That was a very novel idea back then. Because back then the idea was that you need a highly designed data center with very good climate control, very good computers. So doing it in shipping container with outdated hardware was rather new. Yeah, thing is that's very cheap, it's very flexible, you can ship these things easily, you can connect them very easily, but they are really bad. So one cluster, which is a couple of these racks here, so maybe this might be 2 clusters or so. Google claims that for a typical cluster with several racks, in the first year they have a couple of days downtime because of overheating. Then they have at least one failure of the central power distribution unit. So basically the whole container goes down and all machines in that container die instantaneously, and it takes a couple of hours until it becomes back. Then they move around the rack a little bit, which is not too bad because you know that up front, so you can plan for it. But still, around 500 to 1,000 machines just disappear and are not there for a couple of hours. Then you might rewire the network all the time and improve the network infrastructure, which will always kill around 5% of the machines. So 5% of all machines are never working because somebody is doing repairs and changing them. And that's just, the overall thing. Then you have rack failures, 20 rack failures per year, which means without any notice, 80 machines just disappear, and it takes, well, half a day, a quarter day, 6 hours, 1 hour to get them back. Then you have what Google claims going wonky. Basically, racks just performing not properly, packages getting lost, stuff doing not what it's supposed to do, and nobody actually knows why and how. So, this typical computer problem where a computer just doesn't work and there's no proper explanation for that. Network maintenance, router failures. For router failures, basically the whole traffic breaks down for a thing. Machine failures, and not talking about hardware failures. So basically hard disks fail all the time. And it's quite interesting. A couple of years ago I tried to find statistics on hard drive failures, and it was quite interesting that producers of hard disks don't have proper statistics about hard drive failure rates because they do just in-lab testing. So basically they take a hard drive and do artificial agent and just, mistreat the hard drive with hot air and cold air and bang on it with a hammer and then extrapolate on how long that hard drive will usually last based on the abuse they did in a couple of weeks. And it was quite interesting that one of the only studies, large-scale studies on hard drive failures was available by Google, who claimed we have something like 100 million hard drives and we were running these things for a couple of years. This is how long these things work. And it was really surprising that for Google, the average lifetime of a hard drive is 3 months, which is significantly worse than what you're used to from your hard drives, I guess. The reason for that is these hard drives are running 24/7, so basically they're running all the time. They're running under extremely high load, and Google doesn't really care about cooling these things. So they are running the machines and hard drive hot because climate control is extremely expensive. So a good climate control costs you billions, and Google claims it's cheaper repairing broken hardware than actually doing proper climate control. Yeah, then your hard drives break, after 3 months with 1 million servers. So basically, that thing is broken all the time. It's one of the most shittiest data centers there is because it's always broken. Still, Google usually works. I mean, it's very rare to have Google servers not working, and when a Google service does not work, then it's usually because somebody messed up and not because, well, the system behind it is not working. Why is that? Well, that's mostly an achievement to the system design. It's the software repairment. And we will cover a lot of software which is running behind that. So mostly it will be stuff like a Google file system, which is a highly distributed and robust file system. We will cover Google Bigtable, which was the first try to build a database on top of that. So a database which you can build on its infrastructure like that, and which is still works. We will cover Spanner, which is a new version of the Google database, because that's quite funny, the story, because What you did with the new with these cloud databases like Google Bigtable, you removed all proper database features. These things didn't support transactions, for example. And that was fine for a couple of years. But then people realized, okay, you know what, transactions are really important. And now you have to reintroduce transactions into these new databases. And yeah, Google spent as one try of trying to bring back proper database features. Good. So we talked about that. So basically, what will we do in this lecture overall? We start with distributed classical databases with the old school approach of designing it. We will talk about proper database features like transactions, query languages, schemas, optimization, and so on. We will show how this is limited, highlight the features like, well, what you actually want to have in modern systems like elasticity and scalability. Then we do a big jump to peer-to-peer systems, which is the complete opposite of distributed databases, so overlay networks and stuff. And then in the end, we will bring it together into cloud storage and NoSQL systems. So where the main goal is to have a cheap, large-scale data center running data storage. This is focused on low-end hardware, high hardware elasticity, but you pay for that by a limited feature set, by limited query capabilities and other things. So that covers stuff, like DB, for example, or HBase, Bigtable, maybe a little bit Cassandra or CouchDB. So basically these newer systems. So basically, what you should probably remember from this lecture is that we have this trade-off field between number of features we use or need. So database features like data modeling, query power, storage guarantees, transaction support, and, well, soft requirements, stuff like network and hardware features, elasticity, extensibility, flexibility, volatility. And we have distributed databases being here, having many features with very low flexibility and scalability. We have peer-to-peer on the other corner, and cloud is somehow the thing in between which brings everything together. Good. That is it for today. Next week we will start with a lecture for real with data partitioning and data sharding. So basically how to distribute data in a classical distributed database. Okay, thank you for today. See you next week.